A very important application of Fourier transforms in image processing is frequency filtering. There's a Colab notebook that goes along with this lecture, and the link for it will be provided in the description of this video. So what is frequency filtering? In signal processing, a low-pass filter is one that allows the low frequencies to pass through but suppresses the high frequencies. For example, removing the high frequency hiss in an audio signal is an example of a low-pass filter application. A high-pass filter is the opposite. It allows the high frequencies to pass through and suppresses the low frequencies. For example, removing the low frequency hum in audio signals uses a high-pass filter. A bandpass filter allows frequencies between a low and a high threshold to pass through and suppresses all other frequencies. So, for example, an FM radio receiver uses a bandpass filter centered along a particular frequency to isolate the desired channel while rejecting all the other frequencies outside of its bandwidth. These definitions are: pass band refers to the frequencies that are allowed to pass, and stop band refers to the frequencies that are not allowed to pass. So remember, images are just two-dimensional signals, and we can certainly apply low-pass, high-pass, and band-pass filters to images. In fact, we often do that implicitly in the spatial domain when we convolve an image with certain kernels, such as a Gaussian or a difference of Gaussian or Laplacian of the Gaussian. We're actually doing bandpass filtering. For example, a low-pass filter is implemented in the spatial domain by convolving with a Gaussian blur or an averaging filter, and its effect is that it smooths or blurs the image. We use that in noise reduction, smoothing before downsampling, or background extraction from images. A high-pass filter in the spatial domain is implemented by convolution with the Laplacian or Sobel operator, and it emphasizes the fine details and edges of the images. It's used for edge detection, image sharpening, and texture analysis. And a bandpass filter retains intermediate frequencies. In spatial domain, we can implement it with a difference of Gaussian operator, and it allows us to isolate features. We use it in multi-scale analysis, such as Laplacian pyramids and texture segmentation. But instead of doing all this kind of indirectly in the spatial domain, we can do it directly in the frequency domain using Fourier transforms. And that's what we're going to implement here. We're going to implement this function that is a Fourier bandpass filter. Its goal is to create a circular mask of a certain radius in the frequency domain that's centered on the DC component. And this circular mask will allow some frequencies to pass and others to be set to 0. The parameters that our function will take are, of course, the image and a lower cutoff frequency and an upper cutoff frequency threshold. So if we just specify the upper cutoff frequency, we will create a low-pass filter that will allow all the frequencies below this to pass and suppress everything above it. If we specify only a lower cutoff frequency, it will create a high-pass filter that will allow only the frequencies above the cutoff to pass and suppress everything below it. And if we specify both lower and upper cutoff frequencies, then we create a bandpass filter. So the question is, what are these cutoff frequencies? How do we know what numbers to plug into these parameters? Well, that depends on the size of the image. The cutoff frequencies are expressed as a radial distance from the DC component, which is the center of our magnitude spectrum. And if you recall, the highest spatial frequencies in our magnitude spectrum are the ones that occur at the farthest corners of the magnitude spectrum. These are called the Nyquist frequencies. And so the maximum radius that we can specify is half of the width squared plus half of the height squared, the square root of that. And for example, for a 512 by 512 image, the maximum radius is about 362, which means that we can safely pick our lower and upper cutoff frequencies anywhere in the range of 0 to 362. Finally, in the code below, we will compute a radius that will compare to the cutoff frequencies in order to create our frequency mask. And this is the formula that we will use for implementing the radius, where u and v are the frequency coordinates in the Fourier transform image, and r is the radius as a function of u and v. So let's implement our function. Here we're going to use CV2's Fourier transforms. The function takes the image, it takes a lower cutoff and an upper cutoff frequency. By default, the lower is set to 0, the upper is set to none, and if we don't change the default, our image will simply go through this without being filtered and will return the original image. So first, we need to ensure that our image is in a float32 data type as required by CV2's discrete Fourier transform. Next, you simply submit the image to CV2's discrete Fourier transform, and you remember you have to set the flag that gives us the complex output, because we need both the real and imaginary components of the output. And then you use NumPy's shift function to shift the DC component to the center of our magnitude spectrum. Next, you hold this over here, you create your frequency grid. The image has a shape, you take the rows and the columns, you create a mesh grid to create the U and V frequency indices, and you simply plug in U and V into this formula that I gave you, and you have M and M, which are the number of rows and columns. You have U and V that you have computed with your mesh grid, and you end up with the radius. Then you create your binary mask. Basically, this mask says that if the radius is greater than the lower cutoff and less than the upper cutoff frequency, the mask has a value of 1, and if it's anything else, the mask has a value of 0. So this is a binary mask, which is a very sharp mask, and we'll come back to this. You apply the mask to both the real and imaginary parts of your Fourier transformed image, and you do that simply by multiplying the mask by the appropriate channels, 0 and 1 for the real and imaginary parts of the Fourier transform. And then you inverse shift the Fourier transform, and you compute, and then you submit the inverse shifted Fourier transform of the masked Fourier by using the CV2's inverse Fourier transform function. Again, you set the same flags as before. You want the output to be real, and you want it to be scaled, that is divided by the number of pixels, as you always do in inverse Fourier transforms. So this is your filtered image. Just for the purpose of visualization, we also want to display our magnitude spectrum. So again, remember that you have the real and imaginary components of your Fourier transform. You can submit that to the CV2 magnitude function to create a raw magnitude spectrum. You add 1 and you take the log of it to create a displayable magnitude spectrum, and you return these. So when we use this function that we have just created, here's our original image. Here is the Fourier transform of the image without any filtering. Now, when I apply a low pass filter, here I've specified an upper cutoff frequency, but the lower cutoff remains at the default value of 0. So I'm allowing everything in the frequency range between 0 and my cutoff, which happens to be an upper cutoff of 40 here, to pass. So U between 0 and 40 and V between 0 and 40 are passing through. These low frequencies are passing through, and all the higher frequencies are set to 0. And that results in blurring of the image. So a low pass filter that's only allowing the low frequencies to pass causes blurring of the image. And the opposite is here. Here I have specified a low cutoff of 20, and haven't specified a higher cutoff in our function. So it's allowing everything above 20 to pass through and suppresses everything below 20, sets those to 0. And this is a high pass filter. It's allowing the high frequencies to pass, and it results in detecting the edges of the images, highlighting those images. So that's a high pass filter. For a band pass filter, you specify both a lower cutoff and a higher cutoff. It allows the frequencies between those cutoffs to pass through and suppresses everything else. And that allows you to create these feature isolation or feature selection images that we can, for example, use in our Laplacian pyramids. So let's compare this to what can be achieved by convolution in the spatial domain. You can refer to what I did in the Colab notebook to get these images, but basically this is our original image. Here I applied a Gaussian blur that blurs the image that looks very similar to our low pass filter. Here I created a high pass filter by simply subtracting the original image and the Gaussian image, and that looks similar to our edge detector high pass filter. And then I created a band pass filter by convolving with the difference of Gaussian kernel, and that looks very similar to our band pass filter implemented directly via Fourier transforms. There is a big difference between these sets of images though. Here we have a lot of artifacts. You see all these things are ripple artifacts that occur in these images but not in these images. And the reason they occur is because the type of filter we have implemented through that function is called an ideal filter. What that means is that it enforces a very sharp transition in the frequency domain from 1 to 0. It's a binary mask. And that sharp transition propagates from the frequency domain into the spatial domain as ringing or ripple artifacts that we see here, and that's obviously undesirable. And this is what we call the transfer function for an ideal filter like the one we have implemented. Everything in the desired frequency has a mask value of 1 and otherwise has a mask value of 0. But we want something that allows a more gradual transition in the frequency domain in order to get rid of these ripple artifacts. And the solution to that is the Butterworth filter. Butterworth filter is the type of frequency domain filter that provides a smooth transition between the pass band and the stop band. And the way it's implemented is that it has a different transfer function from our binary transfer function here. For a low pass filter, we use this function. For a high pass filter, we use this function. And for a band pass filter, we use both of them. In addition to having our radius and upper and lower cutoffs over here, this has another parameter called n, which is the order of the filter, and it controls the sharpness of the transition. So n equals 1 produces a very gentle roll-off in the transition in the frequency domain, whereas a higher end produces a sharper but still smooth transition. So what's next is that you're going to do this yourself. You're going to implement the Butterworth filter according to these formulas for the transfer function, and hopefully you will end up with this. You will see that, first of all, after applying the Butterworth filter, we no longer have any ripple or ringing artifacts. And secondly, we have these smooth transitions in the frequency spectrum as opposed to the very sharp and abrupt transitions that we had with our ideal binary filters.